This is Engineering Mechanics Statics, Module 1, General Principles. The chapter objectives of this module include an overview of basic quantities and idealizations of mechanics, a review of Newton's laws of motion and gravitation, SI units, procedures for performing numerical calculations, and a guide for solving problems. There's a short quiz for you to attempt at the end of this module. The chapter outline also aligns with the essential text, Engineering Mechanics, or the custom text for this unit. Mechanics can be divided into three branches: rigid body, deformable body, and fluid mechanics. Rigid body mechanics deals with statics and dynamics. I am your lecturer for the statics part of this unit. Statics deals with bodies that are at rest or moving with a constant velocity. Having said that, the area of specialization that I'm involved in, structural engineering, we tend to prefer our bodies to be at rest. Generally, if they're moving with a constant velocity, something has gone terribly wrong. Dynamics deals with the accelerated motion of bodies. The basic quantities that we use in engineering are length, mass, time, and force. It's important that you understand the definition of these basic quantities. When we're dealing with engineering, we have to make certain idealizations to apply the fundamental principles of equilibrium and Newton's laws. One of those idealizations is that a particle has a mass and size which can be neglected, and that a rigid body is a combination of a large number of particles. What does that mean in engineering terms? Consider the image in the top right. In this, we're at a site visit to a precast concrete yard, and the precast concrete wall panels are being lifted by chains which go up to a hook. If we were to draw a free body diagram of this hook and pulley system, we would represent it as a single particle and ignore its mass and size. The free body diagram of this connection would be representing the forces exerted by the chains which are supporting the precast panel. The hook itself is ignored in terms of its mass and size, even though in reality the hook has a considerable mass, maybe 25 kilograms, and it certainly has a physical size or dimension to it. Another idealization that we make is that of a concentrated force. The effect of a concentrated force is considered to be acting at a single point. If we consider this steel rail and a steel wheel sitting on the rail, we would consider that force to be transmitted through one single concentrated point. In reality, there is a physical dimension to the contact surface of the rail and the wheel, but we idealize this to be a single point load. Newton's laws of motion are probably quite familiar from your previous studies, but let's recap the first law, which is that a particle originally at rest or moving in a straight line with constant velocity will remain in that state unless it is acted upon by an unbalanced force. If it is acted upon by an unbalanced force, it will experience an acceleration that has the same direction as the force and a magnitude that is directly proportional to the force. From this principle, we generate the expression force equals mass times acceleration. And finally, there are mutual forces of action and reaction between two particles. These forces are equal, opposite, and collinear. We use this principle to help determine reactions. Newton's law of gravitational attraction is expressed here. If we replace weight with g m, mass of the Earth, upon r squared, and we express g, or gravity, as this universal constant of gravitation times the mass of the Earth upon r squared, we get the simplified expression for weight, which is weight equals mass times gravity. SI units are used in engineering. 3 of the units are called base units, and the 4th unit is derived from the equation. The SI system of units includes meters, seconds, and mass in kilograms. The force unit, Newton, is derived from force equals mass times acceleration. The table in your textbook expresses these base and derived units. At a standard location, gravity is 9.80665 meters per second squared. But for calculations in engineering, we use gravity equal 9.81 meters per second squared. Therefore, the mass of 1 kilogram has a weight of 9.81 newtons. Generally, in society, when people say, "How much do you weigh?" they are not correctly responding because we answer with our mass of so many kilos. What does 1 Newton force really mean in terms of your body weight? For a very large or small number, we can express it using a prefix. For example, 4 million newtons we would express as 4,000 kilonewtons, or 4 meganewtons. This table 1-2 in your text summarizes the exponential form, the prefix, and the SI symbol. It's important to express your answers in this exponential form and to remember all of the standard prefixes. When you are doing calculations, an easy way to ensure that you are doing them correctly is to write the dimensions of each unit. Regardless of how the equation is evaluated, it is going to maintain dimensional homogeneity. All terms can be replaced by a consistent set of units. Significant figures refer to the accuracy of a number. A significant figure is any digit including 0. For example, both of these numbers have 4 significant numbers, 5,604 or 34.52. But when a number begins or ends with 0, we make use of the prefixes to clarify the number of significant figures. For example, 400 as one significant figure would be 0.4 by 10 cubed. However, if we wanted 400 to have 3 significant figures, we would express it as 0.400 by 10 to the power 3. We round off numbers to an appropriate number of significant figures. Generally, that is no more than the accuracy of the problem, or 3 significant figures. When you are doing your calculations, retain the greatest number of digits for accuracy, carry those through all your calculations, and then round off the final answer. This is a general procedure for analysis. In this general procedure, you relate the physical situation with theory, draw diagrams, particularly free body diagrams, tabulate the problem data, apply the appropriate formulas, solve the equations, check dimensional homogeneity, and report your answer to the appropriate number of significant figures. The last step, 6, technical judgment and common sense, is often overlooked, but it is crucial that you check your answer. Ask yourself the questions: does it seem right? Is it what I expected? Is it reasonable? Your calculations should look neat, logical, clear, and easy to follow. They might not look like that to begin with, but start practicing and it will serve you well, if for no other reason to get credit for your work. This IPE approach, interpret, plan and execute, is a good idea to keep in mind when you are approaching problems. Read and reread the question. Think about what is being asked for. Plan out the steps to get to that answer. Execute the necessary steps and assumptions. Explain what you're doing, and then reflect on your answer. For example, let's convert 2 kilometers per hour to meters per second. In order to change kilometers per hour, we need to multiply by how many meters there are in a kilometer and convert the per hour to seconds. So 2 kilometers per hour we multiply by 1000 meters. This is meters per kilometer. The units or dimensions of kilometer will cancel out. We then multiply by 1 hour, which is 3,600 seconds. The hours cancel out and leave our final answer in terms of meters per second. On our calculator, we probably had numerous digits, but the answer is expressed here to 3 significant figures. The question is actually given as 2 kilometers per hour. That is 1 significant figure. So if we were to express our answer consistent with the question, we would express it as 0.6 meters per second. There's a short quiz now on Module 1